Today we're going to look at standardization and the 68, 95, 99.7 rule. Okay, so for any normally distributed random variable, and remember, it's got to be normally distributed. So this is really important that this only applies to normally distributed random variables. We have approximately 68% of the values lying within one standard deviation of the mean. Okay, so here is the mean. And recall that this is Z is normally distributed. So this is the standard normal distribution with a mean of 0 and a variance of 1. Remember, that's sigma squared equals 1, which means sigma is 1 also. The variance and the standard deviation equal the same value there. So what we have here is we have within one standard deviation either side of the mean, we have 68% of the values. Okay, or another way to think about it is that the area under the curve is between negative infinity and positive infinity is going to be 1. This area here is 0.68 of that. Okay, so let's have a look at how this might work. So what I did earlier was define the function f of x as this function here. Now that, if you recall, is just the standard normal distribution function from the last lesson. So what we're going to do is run a little integral here. So I'm going to integrate between 1 and negative 1 for the standard normal distribution function dx. And what this calculator should tell me now is that the answer is roughly 0.68, roughly 0.682. Okay, so I can find that out by using the 68 rule, so 0.68, or I can integrate to get this value. All right, what else? So 95% of the values lie within 2 standard deviations of the mean. So if you fall within 2 standard deviations of the mean, you are basically part of 95% of the population, okay, if the data is normally distributed. Okay, and we can do that again by changing the terminals here. And what should happen is I get 0.95, so 95%. Now 3 standard deviations encompass 99.7. So if I change this to 3 and 3 and get the area under the curve, I'm pretty much getting everything. Okay, in this case 99.7. Okay, now remember, if I go from positive infinity to negative infinity, I'm going to get 1. Okay, well in this case I can't get like an exact value on it, but it's pretty much 1. Okay, so basically, if I go from 3 to negative 3, I'm pretty much getting all of the values, in fact, 99.7. Right, and all normal distributions are spread this way. So it allows us to generalize fairly quickly that if we get the mean and standard deviation of data that's normally distributed, we can apply this rule, okay, and we can know how or where the values lie. Now this particular graphic then allows us to split the normal distribution curve up into certain areas. Right, so if I know that 68 are 1 standard deviation at either side of the mean, that's going to be 34% 1 standard deviation above the mean, or 34% 1 standard deviation below the mean. Okay, now the other thing I know is 2 standard deviations is 95. If I remove 68 from that, I'm going to be left over with 2, oh my God, I can't believe I'm doing this, but 95 take away 68, what the hell? 27, okay? So that means that this area here and this area here must be 27, and half of 27 is 27 on 2, or 13.5, okay? So that means that this area here, between 1 and 2 standard deviations above the mean, is 0.135. This one here would also be 0.135 by symmetry. Right, this symmetry is really important when it comes to understanding how the normal distribution curve works. Plenty of questions involve this idea about symmetry. And basically, if I get something like 68%, okay, that covers that. Now, if it's 95%, we say most probably or most likely. Okay, so values, if we get 0.95 or a probability of 0.95, we say most probably or most likely, and 99.7 is almost certainty. So with normally distributed data, we can say with almost certainty that the value will fall between plus or minus 3 standard deviations of the mean. Right, so let's look at how this relates to VCE. Scores obtained on a VCE subject can be assumed to be normally distributed with a mean of 30 and a standard deviation of 7. Okay, in fact, they have to be. So approximately what percentage of the distribution lies within 1, 2, or 3 standard deviations of the mean? So what I think you should do at this point here is anytime you work with normal distribution curves is you should actually graph them. I quickly knock them together like this. Here's mu. Okay, now I know that this is not the greatest curve ever, but it will do the job for us. And so mu, or the mean, is 30. Let's go 1, 2, and 3. All right, so this is going to be 37 because I'm going up by 1 standard deviation. Now 2 standard deviations is going to be 44, 51, 30, 23, 16, 9. Okay, so approximately what percentage of the distribution lies within 1, 2, or 3 standard deviations of the mean? Right, so if you score between, so 68% are within the scores 23 to 37. That covers 68% of the cohort, okay, between 23 and 37. 95% of the cohort are within 16 to 44. Okay, so we've got most students falling somewhere between 16 and 44, and 99.7 are within 9 to 51. Okay, and that's going to cover pretty much everyone between 9 and 51. So note that the total area under the curve is 100%, or all of them. So all students will fall under the curve. Okay, but again, there's a 0.3% chance that you fall either below 9 or above 51. Okay, from the example on the previous slide, 95% of the scores in the VCE study score distribution lie between 16 and 44. That is within 2 standard deviations of the mean. What percentage of the distribution is more than 2 standard deviations above or below the mean? In this instance, less than 16 or greater than 44. Okay, so again, what we'll do is we'll quickly draw up our distribution curve. That's a better one this time. So we've got 30, 1, 2, 3, 1, 2, 3. All right, so 37, 44, 51, 23, 16, and 9. Okay, in this instance, less than 16 or greater than 44. So less than 16 will be this part here, and what I do is I colour them in, and more than 44 will be that part there. So remember that all of the scores, or 100% of the scores, are under the curve, and what we're going to do is chop out the middle 68% and the 13.5 and the 13.5, or let's remove 95% of the scores. And what that will leave us with is this coloured part here, okay, which is 5%. All right, so what percentage of the distribution is more than 2 standard deviations above or below the mean? It's going to be 5%. 2.5 above, 2.5 below. All right, so example, and again, I've just ripped this off Tenchi's PowerPoint here, but always draw a picture. If X is normally distributed, so it's important to note, it's normally distributed, and the probability that the random variable being less than a particular value, A, is 0.2. All right, so let's draw that up in a curve, okay? And what I'm going to do is 0.2, so the probability of a value being less than that is not much. That's like 0.2, okay? So I'm going to let A be around about here, and note that this part here is 0.2. That'll be the area between, if I integrated between A and negative infinity for the normal distribution curve, what I'll get is 0.2. That's that area there. All right, and the other thing they tell us is B is less than 0.7. Okay, so what I'll do is I'll just change color so that this has a bit more effect. Right? And so 0.7 is a fair bit of the curve. In fact, it doesn't include this top 0.3. So I'm going to start it here. Ooh, that's pretty bright. That'll be all of this stuff here, including that stuff as well. So that's 0.7, and this other one, no, it's not the same color, but it doesn't matter. 0.2. All right, let's answer some questions. So they want to know what's the probability that the random variable is between A and B. So basically they want to know what this area here is. In effect, that's saying, hey, can you get me the area under the curve between B and A for f of x dx, where remember f of x is the standard normal dist curve. Okay, and yeah, I can, because if I know that this part here, all of that part there is 0.7, I can simply remove the 0.2 from the 0.7. So 0.7 take away 0.2, that equals 0.5. So this one here must be 0.5. So between A and B we have 50% of the values. Right, what's the probability that it's less than A? So less than A, given that it's less than B. Right, so less than A is 0.2, okay, and we know that it's not out of or divided by 1, not divided by all of it, but we're shrinking the sample so it's out of this. This one is going to be the probability that the random variable is less than A over the probability that the random variable is less than B. Now this is because this is what we know. It's not over 1 anymore. It's over what we know is the probability. So that's going to be 0.2 over 0.7, which is 2/7. All right, if x, a random variable, is normally distributed, important to know, and the random variable greater than d is equal to 0.16. All right, let's draw that. Not the world's best normal distribution curve. Greater than d. All right, so let's pop d somewhere there and indicate that this shaded portion is 0.16. You might be wondering how I know it's there. That's just a complete approximation. Like I know that the area under the curve between negative infinity and positive infinity is going to be 1, that the area under the curve between 3 and -3, so 3 standard deviations to the left and the right, is 99.7% of the values, right? So this is only 0.16, so it's not much of the curve, so I'm only going to highlight that. So I'm just guessing, but it's probably roughly right. All right, and between C and D, so the probability that the random variable falls between two other values, C and D, is 0.59. So it's going to go roughly that green part there. So there's C is 0.59. All right, find probability less than C. All right, yeah, can do that. So the picture will tell us that we're after this part here, which means that if we start with 1, all of it, so the probability under the curve, and then remove this part here and this part here, we're going to be left with this part here. So 1 take away 0.59 plus 0.16 is equal to 1 take away 0.75, 0.25. Find an approximate answer for Z if the probability that the random variable greater than D, so on this curve, I know that the random variable is greater than D is 0.16. We want to know when that would happen. For what value of Z would that happen here on the standard normal distribution curve? Remember, that's what we're talking about there, Z. Z is the standard normal distribution, and there it is, it's defined. All right, so I know a little bit about the value breakup of the normal distribution that you won't be super familiar with yet. All right, so I know that this part here, that's 68%, that should be familiar to you. This part here is 50%, and this part here is 34. Okay, so 1 standard deviation to the left and the right is 68, 1 up is 34. Okay, now notice that that's going to be 34 and 50. So 34 plus 50 is equal to 84. 100 take away 84 is equal to 16. That's this part here, okay? Or in other words, 0.16. So my guess is that Z, this will be when when Z is greater than 1, okay? So Z in this case is equal to 1. Right, now let's just check that to see whether we are right. So what I'm going to do is integrate, starting at positive infinity. I'm going to come all the way down to 1 standard deviation above the mean. I've still got f of x defined as the standard normal distribution. And what the answer should say now is 0.16. Yeah, that's not bad, 0.158, okay? There's another way of doing this. So what you could do is integrate. Now, I don't think it likes positive infinity, so I'm going to give it a maximum value of 5, like all the way up here, 5, between 5 and an unknown value for the standard normal distribution curve. And I want that to equal, so just check your cursor there, make sure you hit right after the dx to get the big cursor, equals 0.16 for d. So I'm going to solve that for d. And what it should do is give me a value of d equals roughly 1, okay? So they're going to say you basically, the area under the curve between 5 and 1 on the standard normal distribution. Now, why 5? 5's up here, so that's going to just encompass all of that to get us a pretty good approximation of that. So let's just see what it says. Yeah, 1. Okay, 0.99 or 1. Now, why did I use 5? Right, why not positive infinity all the way down to d? Because I think it doesn't like it. I think the calculator is going to throw a hissy fit. Yeah, it doesn't like it. So you can choose like 100. No, it doesn't like it for 100. Oh, it's crashed. It's crashed on 100. Oh, here we go. It's got that cycling thing. So remember, when you get that, it's really struggling with this. It's really struggling with the processing. Let's hit escape. All right, because what it's doing basically is the calculator has gone up to 100 on this normal distribution curve, and it's calculating all of these little areas here and sticking them all together. So that's why it doesn't like that. It seriously bucks at infinity. It goes, I'm not even going to try this. 100 it doesn't like. Just curious. 50, will it start to? Yeah, it doesn't like 50 either. Cycling away. So, but if you get close, like remember, 3 standard deviations above is 99.7. This is going to almost get it. So this should be really close, okay? And just to be sure, go another standard deviation above, and it's just going to get closer and closer to that one value that we're looking for. All right. So when we standardize, from the previous 2 examples, the standard deviation can tell how well a student has done. Now, the previous 2 examples are the ones on the VCE. How well a student has done in a particular subject. If they get a 37 for a subject, then this puts them in the top 16% of the state. It's pretty good. Okay, so if you get a 37, you basically sit here, 1 standard deviation above the mean, which means that you are basically within this group here. Okay, and that's what we did in the last part there. That's 50%, 34%. So you're above 84% of the state if you get a 37. So pretty impressive. Nothing to scoff at getting a 37. If you got a 44 for a subject, put you in the top 2.5%. Okay, so that is 1 standard deviation more, which means that, yeah, you're really, really in the top section. Because of the additional insight provided by the standard deviation of a normal distribution, it's usual to convert normally distributed data to new sets of units which show the number of standard deviations each data value lies from the mean of the distribution. And what we call these are standardized values, or Z values. If you're further maths, we call them Z scores in further maths. All right, so here's how it goes. What we do is we use a bit of a process. We first subtract the mean of the normal distribution or normal random variable from each score and then divide by the result of the standard deviation. And why standardize? There are two reasons to do it: to compare different distributions more easily, to find an unknown mean or standard deviation. So we'll look at this first example to compare distributions. So I'm going to explain what that means. So here's Susie. And what she did is that she obtained results in two subjects shown below. In art history, she got 70. In poll, she got 85. What's the better result for Susie? Well, you'd sort of go, obviously, it's like the 85, the higher number, okay? But it doesn't quite work like that, okay? And that's because what we've got to do is consider what the mean of the subject was and what the standard deviation of the subject was, okay? And I actually got, like at uni, it's really hard to get an 80% or above score. It doesn't happen often. It's called a HD at Monash, or it was back in like the late 90s. That was called a HD if you got 80% of above or above. And I actually did it twice, once in a math subject, which surprised me a little bit because I sort of was struggling in that a bit. One in another subject called professional communications. And whilst I should have been happy with that, and I was happy with the 80%, the subject was a joke. It was so easy. And that year I did scrape by in another subject called object-oriented programming. I got a 54 in that subject. All right, now what was the better result? Well, I'll bet you it was the 54 in object-oriented programming, because in that lecture, or in that one, I remember the first lecture, the professor told us that basically 1 in 3 students fails the subject. Which is a great way to start. A uni subject is 1 in 3 of you will fail. I hope the times have changed at Monash, but that was a little scary. I did scrape by with a 54, okay, but I still to this day reckon it was better than my very cheap 80 in professional communications. That subject was a joke. All right, I digress. Now let's go back and find out how Susie has gone. Okay, so find the standardized mark in each subject and hence determine which subjects she did better compared to everyone else. All right, so to do it, what we do is we take the score that she got, the mark, so we go 70, okay, and so we're going to work out her Z-score, okay, 70, take away the mean over the standard deviation. And what that's going to do is basically tell us whether she was, or how many standard deviations she was above or below the mean. All right, so we're going to do this on the calculator. So it's 70 take 60 is 10 over 4.5. And let's get, so equals 2.222 dot, 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 dot. So basically we're saying that she sits between 2 and 3 standard deviations above the mean, okay, which is very good. All right, as we established earlier, that's like the top, I can't remember, 2.5%. So this is how she went in art history, old paintings and stuff. All right, so poll, not easy by any stretch. 85 take away 73 over 5.4. So what we're going to do is work out our Z-score. Okay, so that's 85 take away 73. Evaluate that over 5.4. And her Z-score is, oh my goodness, it's exactly the same. All right, so that's poll. So while she may hang her head in shame over her art history result, oh, I got a 70, I got a 70 compared to poll, I did much better in poll, but actually she's done the same. Okay, she's achieved very well in each of those subjects, top 2.5% in both of those subjects. Okay, so between 2 and 3 standard deviations. So here is the formula that I was using there. So standardized value is data value. So that's the data value there. Take away the mean, which is 60, over the standard deviation. That's the symbol that we use. Now, remember, this is probably what you want to stay away from, okay? So if you got a negative score out of this, that means you're 2 standard deviations below the mean, okay? Now, nothing wrong with it, okay? But you probably for subject scores anyway, if you're doing a uni course, would rather be here than 2 standard deviations below the mean, although I was just happy sometimes at uni passing. Here's what would happen to a student who got a study score of 23. All right, so remember in the VCE, we have a mean of 30 for every subject, standard deviation of 7. So let's work out what her Z score was. 23 take away 30 over 7 equals -7 over 7 equals -1. That means she's 1 standard deviation below the mean, okay? Or she is in the bottom, or he is in the bottom, what would it be? 16% of the cohort. That's what that would indicate, bottom 16%. All right, so your job now is to try that out in 16B.